Now that we have our methods for taking the antiderivative, let's go back to our definite integral. So again, previously when we did definite integral, it was looking more geometrically as area under the curve, and this absolutely still does represent area under a curve. In fact, we'll go through an example where we tie it back to that. But now with our ability to take the antiderivative with our formulas, we can also calculate it algebraically without having to graph it, which will be convenient. So if we are taking the antiderivative from a to b of f of x dx, what we're going to do is take the antiderivative at b minus the antiderivative at a. So what we're doing is we're taking the antiderivative across an interval a to b, and what we're going to do is plug in the largest value into the antiderivative first, and then subtract the smaller value. So let's say we wanted to evaluate the definite integral from 1 to 3 of x dx, and we're going to do this two ways, using a sketch and then using the antiderivative. So using a sketch, what we would want to do is graph the function x, which would look something like this. And let's see, we're going to look from 1 to 3, so let's go 1, 2, 3, 4. And then our y values are going to match, 1, 2, 3, 4. Okay, so what we're doing here is we're starting at 1, ending at 3, and we want the area between x and our x-axis. So I'm just going to kind of draw a little grid here, and I'm just going to count up the squares. So we're ending up with here is kind of a trapezoid. So we get 1, 2, 3 whole units and 2 half units. So if we're evaluating the antiderivative from 1 to 3 of x dx, that's going to be that area underneath, which is 4 units squared. Okay, so with that, not too bad, but as you can imagine, as the functions get more and more complicated, like as we saw with parabolas and things like that, we had to use estimations. What we want to be able to do is get exact values, and that's what our antiderivative is going to help us with. So using our rule from up above there, if we're taking the antiderivative from 1 to 3 of x dx, there's a lot of different notation out there. What I like to use is kind of these two big brackets. And what I'm going to do is just take the antiderivative of x. So that's going to be x to the 1 plus 1, which is 2, and then we need to divide by that exponent of 2. So there I just use the power rule for taking the antiderivative. Then just to the right of the brackets on the right-hand side, I'm going to put 1 in the lower right corner, 3 in the upper right corner, just so I can still see the range that I'm working with. So we're working with this x squared over 2, and we want to evaluate it from 1 to 3. So what we're going to do is we're going to have two calculations. So we're going to first plug in 3, so that's 3 squared over 2. And then I'm going to subtract, and then parentheses will be really helpful here, especially with more complicated antiderivatives. We want to make sure that subtraction distributes through, but I'm going to plug in 1, which is 1 squared over 2. So we have 9 halves minus 1 half, which is 8 halves, which is 4. So with that, we didn't need the graph at all. It's just a matter of taking the antiderivative function and evaluating it over that range, taking the plugging in of the larger value minus plugging in the smaller value. Okay, let's go through a few more examples with this. So let's say we want to evaluate the antiderivative from 0 to 4 of x squared plus 1 dx. So I'm going to kind of set up my brackets and just focus on the antiderivative of x squared plus 1. So that's going to be an x cubed over 3 plus the antiderivative of 1 is just going to be x. Oh, hold on 1 second. What happened to our plus c? I left it off purposefully because we don't actually need it. But let me prove to you why. And this is just true with our definite integrals. So let's say I kept plus c in there. So I had x squared over 2, and let's say I kept plus c, and I'm evaluating from 1 to 3. So I would plug in 3, so I would have 3 squared over 2 plus c, and then minus 1 squared over 2 plus c. So I'd have my 9 over 2 plus c minus 1 over 2, and that negative would distribute minus c. And that's going to happen every time where we'd have a plus c and a minus c, so it's always going to wipe out to 0. So if we're evaluating a definite integral, we don't need to worry about the plus c, because it's always going to cancel out through that subtraction. It's just when we have an indefinite integral, we always need c, because that could be part of our antiderivative function. But it's just when we're plugging in values, it's going to turn into 0 with that subtraction. Okay, with that, let's go back. So I took the antiderivative, got x cubed over 3 plus x. I'm evaluating from 0 to 4. So I'm going to start parentheses, plug in 4. So this is a 4 cubed over 3 plus 4. And then minus, in parentheses, 0 cubed over 3 plus 0, which is just going to be a big 0. So let's see, we're going to have 64 over 3 plus, let's see, 4, which would be the equivalent of 12 over 3. So we're ending up with a 76 thirds. And that would be it. So with these ones where we're evaluating a definite integral, you should end up with just a numerical value at the end. Because again, this is like finding the area under the curve. If I drew a quick picture here, so x squared plus 1 is our parabola opening downward, going through positive 1, and we're evaluating from 0 to 4. So 0 to 4, wherever that is. Let's see, this is going to end up being positive. If we plug in 4 squared plus 1, yes, it's going to be somewhere over there. So what we did here is we found that area. I drew it too quickly. Parabola opening upward. That's why it was strange to me. Opening upward from 0 to 4, and we found the area underneath, which happened to be 76 thirds, and we didn't need to use Riemann sums at all. This is the exact value. Riemann sums would get us an estimation, but now that we can take the antiderivative, we can find the exact area underneath. All right, let's evaluate the antiderivative from 1 to 4 of 2 over x. And if I just rewrite this a little bit so that we can see what we're dealing with, so 2x to the negative 1 dx. So in case you don't remember the rule, when we have x to the negative 1, that's when we're going to bring in our natural logarithm. But I just want to bring up the case of, what if you forget? What if you try to apply the power rule? Well, if you add 1 to that exponent there, you're going to end up with x to the 0 over 0. And dividing by 0 is a big no-no. We don't want to do that ever. So that should be a sign like, oh, if we can't take the antiderivative of that, something's not right. And it's because we can't use the power rule with this one. This rule is specific to the natural log. So what we're going to do is, as we take the antiderivative, we'll still have the 2, and then we'll just be taking the natural log of the absolute value of x to replace that x to the negative 1, and we're evaluating from 1 to 4. So we're plugging in positive values here, so we don't need to worry too much about the absolute value. So plug in 4, so 2 natural log of 4 minus 2 natural log of 1. And we could simplify this a little bit. Natural log of 1, if we remember our logarithms, we're asking e raised to what power would give us 1, and that's going to be a 0. So that's a 2 times 0 over there, so that's going to wipe out. So all we're left with is 2 natural log of 4. And we're done. Okay. Antiderivative from 0 to 2 of 2x minus 2x squared dx. So the antiderivative of 2x is going to be x squared. The negative 2x squared, so we're going to have the negative 2x, and then 2 plus 1 is 3. and then divide that by 3, and we're evaluating this from 0 to 2. So if we plug in 2, we'll have 2 squared minus 2 times 2 cubed over 3, and then we're going to subtract 0 squared minus 2 times 0 cubed over 3, which all of that's just going to turn into a big 0. So we'll be left with a 4 minus 16 thirds, which, let's see, that'll be a 12 thirds minus 16, so a negative 4 thirds. So getting a negative number out, what that means is that the area that we're taking dips below the x-axis. Remember with our definite integrals, areas below the x-axis are coming through as negative. And we could have both positive and negative scenarios. Like maybe it does something like this, where we're starting here and there's a little bit area above, but most of the area is below, something like that. But the total area, the cumulative area, is coming out to something negative, so that would just tell me there's more area below the x-axis than above. Okay, let's talk about some word problems. So find s of t when v of t equals 6t squared. So just as a refresher, s of t is our position function. So that's where the output is a distance given a certain amount of time. V of t is the velocity function, and that comes from the first derivative of t. So that's our velocity function. So that would be something like, it would be a rate. It would be like miles per hour, something like that. So what we're given is v of t equals 6t squared, and we want to find s of t. So we need to take the antiderivative. We need to go backwards here and find our original function. So what I want to do is I'm going to take the indefinite integral of 6t squared, and this is going to be dt since our variable is t. So with that, we'll have 6t cubed divided by 3 plus c, and that's going to be our position function. So s of t is equal to 2t cubed plus c, and they give us information that s of 0 is equal to 4. So what we can do is solve for c by plugging in that coordinate. So we would have 4 equals 2 times 0 cubed plus c, which means c is just equal to 4. So our position function is 2t cubed plus 4. And that would get us to a velocity function of 6t squared, and also has that original coordinate of 0, 4. Okay, one little business application here. So we have a company determines their marginal cost for production in dollars per item is MC of x equals 4 over the square root of x plus 2. So just remember, if we have marginal cost versus cost function, so say c of x is our cost function, then MC of x is the derivative of that function. So that would be like c prime of x. So we have this relationship where we're given the derivative function, and what we want to do is find the cost. So now we want to find c of x of increasing production from 4,000 items to 5,000 items. So we want to see this cumulative change. So this is going to set up a definite integral for us because we want to look over a very specific interval. So what we're going to be doing here is we're going to find this specific cost. It's going to come from the antiderivative from 4 to 5 of our marginal cost function. So that 4 over the square root of x. So let's go 4x to the negative 1/2 plus 2 dx. And we want to evaluate that definite integral, and that should give us our cumulative cost for increasing production from 4 to 5,000. Okay, so the antiderivative will have 4 times x, so negative 1/2 plus 1, so that'll be a positive 1/2, divided by positive 1/2, plus 2x from 4 to 5. And I'm just going to simplify this a little bit, so this is going to be an 8 square root of x plus 2x from 4 to 5. Okay, plug in 5, so this is going to be 8 times the square root of 5 plus 2 times 5 minus 8 times the square root of 4 minus 2 times 4. So let's see, this will be 8 square root of 5 plus 10 minus 8 times 2, so minus 16 plus 8. Oh, no, minus 8. And we could just throw that into a calculator because we want a cost here, and that should be $3.89. So our units are dollars. So notice how the units change, and maybe actually let's look back at our velocity and position function. So like I was saying with velocity, that's miles per hour. Our original function would just be that numerator, units of miles. So that would be our position function, would be some distance. So we would have that here where the marginal cost is in terms of dollars per item. If we take the antiderivative, all we're going to have is dollars left over. So those would be our units.